So I'd like to thank the organizers for giving me the opportunity to tell you about some work that we've done in strained gallium arsenide and layered silicon gallium arsenide composites, studied by sort of not a somewhat unique and unconventional tool called optically pumped NMR. Okay, I just want to acknowledge my coworkers here. The work that I'm presenting is mainly out of the thesis of Ryan Wood, who's graduated, working at Intel now. And it's a collaboration with a theory group led by Chris Stanton and his group, Gary Sanders, Dipta, Saha, and my group, which is now John Tokarski and Lauren McCarthy. She's just was an undergraduate working with us now at Rice University. This work was supported by the NHMFL UCGP program. And I will point out that the instrumentation and NMR probes that were developed as part of this project are available to users who come to the Magnet Lab and put in a time request. So I just want to point that out in case you have any interest in such NMR experiments. I also want to acknowledge our collaborators at the Magnet Lab, the Condensed Matter NMR group, led by Arnil Reyes, together with Phil Coons, and the optics facility that's run by Steve McGill, and of course Greg Bogner, the Magnet Lab director, NSF-funded national lab. Okay, so here's a brief outline of what I'll be talking about today. So for those of you who are not familiar with OPNMR, optically pumped NMR, I have a brief tutorial on that, and then we'll progressively go from bulk gallium arsenide, OPNMR, to strain, effects of strain and quantum confinement introduced in a multiple quantum well structure, and then we'll see if we can understand the photon energy dependence of OPNMR using band structure calculations by the Stanton group. Okay, so normally a lot of times when people think about strain, it's something that's undesirable in the growth of semiconductors and semiconductor devices, but it actually has very important applications. For example, in the CMOS technology, for improvements in the mobility, carrier mobility. Also, strain is vital in strained layer quantum well lasers and also in solar cells. So strain is not necessarily a bad thing. And let's see if we can, what we can learn from NMR in these semiconductor systems. First of all, nuclear spin memory. There's lots of discussion about the potential to use nuclear spins as in memory devices, in spin quantum computing, and the importance of couplings, electron-nuclear couplings, into the decoherence of electron spin transitions. And so also NMR has been used extensively to probe the electronic states in metals and semiconductors for decades now. Nuclear spin relaxation is sensitive to the density of states. And the hyperfine interactions, night shifts, can indicate the electron spin polarization, spin density, and can be used to probe exotic excitations of 2D electron system in quantum Hall regime, such as the skyrmion excitations. But the focus really of this work, present work, is the use of the quadrupolar nuclei in gallium arsenide. There's gallium-69, gallium-71, arsenic-75. They're all fairly abundant, naturally abundant, and they all have spin 3 halves. So if we look at the interaction of the electric quadrupole moment of the nucleus with electric field gradient at the nuclear coordinates, it has this form. And so we have the Zeeman interaction with the field, the interaction with the conduction electron through Fermi contact interaction, and then this quadrupolar interaction here, which is going to be sensitive to strain because bulk gallium arsenide, being a cubic semiconductor, has a 0 electric field gradient at the nuclear coordinates. But as soon as we deform the crystal, then that EFG can be non-zero. Okay, so those of you, the particular type of NMR that we do is Fourier transform NMR or pulsed NMR. It involves applying a brief, few microsecond radio frequency pulse that's tuned to the Larmor frequency of the nucleus of interest. That tips the magnetization down into the transverse plane where it precesses, and we use a RF coil to pick up the oscillating magnetization, nuclear magnetization, and collect that, and it's called the free induction decay, and then we Fourier transform that, and we get the frequency spectrum, in this case just single frequency component. Okay? Now, one of the problems with NMR for application to thin film or quantum structures that these have very few number of nuclei in let's say you take a sub-micron film grown by MBE. Well, NMR is a very insensitive technique. One of the reasons is because of the very unfavorable Boltzmann factor for nuclear spin. So this splitting, even in very high magnetic fields, is on the order of a few millikelvin. So unless you're working at a few millikelvin, you're going to have a fairly, pretty much equal population of spin up and spin down for spin 1/2 here. So this is much more favorable situation. So if we could imagine putting all of the nuclear spins in the same spin state, then we can only have stimulated absorption, no stimulated emission at all here. And we can amplify the NMR signal by 10,000 to 100,000 fold, depending on relative to the thermal equilibrium. Of course, that depends on magnetic field. This situation is also quite favorable. So we may have a population inversion here. And so the signals will actually invert. If we take the frequency spectrum, we'll get a 180-degree phase shift of the NMR peak in this case. But who cares? I mean, actually, it doesn't really matter. We just have this important thing is this hyperpolarized state is increasing the sensitivity and allows us to start to look at these submicron films and quantum well structures. Okay, so this is a photo of the probe. You can see the tuning and matching capacitor for the tank circuit. And here, the coil is flattened out to be the shape of the wafer, semiconductor wafer. And it's mounted on, in this case, a sapphire block with grooves, and we thermally anchor that with a little vacuum grease. And this type of probe is used in the flow crest that where the sample is exposed to the gaseous helium. The way optical pumping works is you take circularly polarized light, and through optical absorption and angular momentum conservation, we transfer we polarize the electron spins. And through spin exchange with nuclei, we polarize nuclei, and those are detected by ordinary NMR. Okay, we also have the studies that we do use a Ti sapphire laser. And since we're interested in the photon energy dependence, John automated the tuning of the laser with feedback to keep a constant power output of the laser. And we can just run automated experiments to point by point map out the photon energy dependence of the optically pumped NMR. And that brings me to the first set of results for bulk gallium arsenide and an explanation of the optical pumping in gallium arsenide near K = 0, where the heavy and light holes are degenerate. If we come in with a laser, it's impossible to not excite both spin up and spin down states in the conduction band. So you can see the relative transition probabilities are in the ratio of 3 to 1. So we're going to get a steady state electron spin of +1/4 for sigma plus light or -1/4 for sigma minus light. The maximum being, so in terms of polarization, that'd be 50% polarization. Would be the maximum polarization you could get here. And if you use unpolarized light, you'll drive the conduction electron spin to 0. Of course, this ignores electron spin relaxation effects. And you won't be able to do optical pumping if the electron spin T1 is significantly shorter than the lifetime, because there'll be time for thermal equilibration of electron spin in the conduction band. Okay, so now here's the model that's been around for decades since, I should have a reference here, but it's early 70s work by a Russian group, Ekimov and Safarov. I should have reference, sorry about that. But the way it basically works, we have a shallow donor here, and we excite the exciton. The exciton can then become trapped or and ionize, and that will tend to localize the electron spin around the shallow donor. What that does is takes the free electron probability density and it peaks it up around the vicinity of the shallow donor. So there's going to tend to be a much faster rate of dynamic polarization in the vicinity of that, and that will tend to orient the nuclei around. And then, of course, that nuclear spin polarization can propagate out by nuclear spin diffusion. The angular momentum exchange is facilitated by Fermi contact interaction. You have the coupling, which depends on the probability density, and then the flip-flop operators that facilitate the cross-relaxation, electron-nuclear cross-relaxation, and the IZ-SE term, which is the static effects giving rise to resonance shifts and line broadening. And then we can write a model for the time dependence, optical pumping time dependence of the nuclear spin, which incorporates diffusion and relaxation effects and cross-relaxation effects here. And you'll note that it depends on the ability to drive the conduction electron spins out of equilibrium. Okay, and so that's why we're able to get optical pumping signals at high magnetic field using unpolarized light, because we drive SE to 0 while S naught at low temperature is appreciable. We have cross-relaxation, just to label the terms here. And so here's the first experimental result that I'll show you. This is a thermally polarized NMR spectrum. It's gallium-71. And it's at room temperature, so you have a single line here. The line actually represents this overlap of the three possible transitions, delta MI equal +1 transitions here. Because there is no strain, these transitions are degenerate. When we do optical pumping, the signal is inverted. It's a consequence of the negative G factor in gallium arsenide. And you see the signal is quite a bit bigger. You have to think that the absorption length above the band gap's less than 1 micron, but you also have some exciton diffusion out to about 3 to 4 microns. So, but you'll see the negative phase is distinctive of the optical pumping effect. The signal is quite strong. You know, this is like a 4 micron layer here. And what we do is we measure the area enclosed by the peak here, typically plot that as a function of the photon energy. Okay, now I'd like to introduce the effects of strain. So as most of you probably already know, the effect of biaxial tensile strain in gallium arsenide with the strain tensor z-axis perpendicular to the plane of the sample will shift the light holes up in energy and the heavy holes down. So what that does is it allows for the possibility for state-selective optical pumping, which now that we don't have any transitions into the spin-down state allows us to achieve, in principle, up to 100% electron spin polarization. So this could be quite this significant effective strain for spin quantum computing, where we need to initialize the system in ensemble quantum computing, where we need to initialize the system in very high polarization state. Okay, so that's another motivation. So now if we strain the sample, what we do, apply the tensile strain, what we're going to do is we're going to shift the plus or minus 1/2 states will shift down, the plus or minus the 3/2 states shift up. So you can see that the central transition here, nu2, is not affected to first order by any strain effect, by application of strain. But yet the satellite transitions, they do split off. And in fact, from that measurement of that quadrupole splitting, we can infer the strain in the sample. So this really provides an in situ strain gauge, which is a measurement of strain within the first few microns layer from the surface of the sample. Okay. Now, we did an experiment with bulk gallium arsenide where we mounted a 320 micron film onto silicon with epoxy, and we used 2 different silicon support widths, a really thick support and a 635 micron support. We recorded their OP-NMR spectra at low field, and they have different quadrupole splittings. So we tried to figure out what could be going on here, and I could ask you any suggestions? What's going on? It's some kind of strain relaxation here. Okay, well, the hypothesis is that the sample bows. So it's just like a bimetallic strip in an old thermostat that is a function as we cool the sample. If the layers are of comparable thickness, then we have a bowing, and that's going to tend to relax the strain, and we can actually see that. Strain measured at the surface of the sample. So we decided to investigate this further by mounting the gallium arsenide onto with different thicknesses thinned by selective etching, and record their OP and MR spectra with constant silicon support thickness but varying gallium arsenide thickness. And you can see that you get a very narrow, relatively narrow signal for the unbonded, unstrained material. And as you decrease the thickness of the gallium arsenide, you start to pick up some broadening and then eventually a splitting that seems to increase as the thickness goes down. And if we do this by optically pumped NMR at low temperature, because of the differential thermal contraction of the two layers, you can really start to get a sizable splitting observed as a function of the thickness here. So you see it's narrow again for the unbonded. We introduce some strain just by bonding it. Then it seems to actually, so it seems to be non-monotonic here. It seems to go down, and then you're not resolving here, and then it gets large again. So there's actually a paper that does an analytical treatment of multi-layer system, composite system. The way the model works is you take customized to our particular sample, bilayer sample. If the two samples start by having the same dimensions, you cool them down due to different rates of contraction. The gallium arsenide contracts more than the silicon. So then what you do is you apply the end forces to bring them to the same thickness again. You bond them together, and then you allow the system to relax or bow. And so there is actually an equation which we used, and you can calculate the strain at the interface. So it just kind of decreases and then levels off. And actually the strain near the surface, you can see actually as a function of the thickness, it actually will change sign. It'll go from along this is plotting along the z-axis, compressive to a tensile. You go from a tensile strain to a compressive strain as a function of the thickness here. You have to remember we're probing just on the surface here, so our measurement is sensitive to the strain really near the surface, within around a few microns of the surface. And this is the rate. This is the results of the calculation for the 5 millimeter block and the 650 micrometer silicon support sample. You'll notice that we plotted this dotted line here indicates that the sign of the quadrupole splitting should change, but NMR can't detect this sign. It's impossible to determine the sign of the quadrupole coupling by NMR. So what we're going to do is we're just going to take the absolute value of the data and compare it with the absolute value of the theory. See, we get reasonably good agreement. There's some, it's not perfect, but we can definitely distinguish from the thin support and the thick support, which relaxes more slowly than the thinner support. So we do think we have a good qualitative, at least, understanding of bowing effect. And that can maybe be useful in devices if you want to engineer a system with particular strain. Okay, now we'll come to the quantum well. How am I doing with time? Just 6 minutes. Okay, I'm going to have to go a little fast through this. 7. That helps. Okay. So one of the problems with NMR, if you grow a multi-layer structure like this with gallium arsenide layers and you grow it on gallium arsenide substrate, is being able to distinguish the signal contributions from the substrate from the signal contributions of the quantum wells. So the approach that we took to this is we take a silicon support, we put glue there, and we flip it upside down, and we glue it, and then we etch away the substrate. So now we don't have any contribution to the NMR signal from the substrate, if that could due to light passing right through the film. But when you cool the whole structure down, you introduce the biaxial tensile strain. This is the actual quantum well sample. This one happens to be doped. It was a quantum Hall effect sample that we had. And I want to discuss the various effects that are beyond the simple model of optical pumping. One is once you're away from k equals 0, the different curvatures of the energy bands here are going to give you a factor of 2 to 3-fold enhancement of the absorption from the heavy holes relative to light holes. For the finite laser line width, you're going to hit a broader range of density of states. There'll be band mixing effects, magnetic fields, quantum confinement, strain, all are going to have an effect. And these effects are going to lift the heavy hole, light hole degeneracy. So, and in the magnetic field, of course, we have Landau levels in a bulk gallium arsenide. We'll still have free motion along the field direction, so we still have 1D density of states. So you get the Landau levels, but with a tail, that 1D density of states tail. In 3D, these tails can overlap, so you can never really just hit the heavy hole or light hole band. But if we're in a 2D system where quantum confinement, we can break the heavy hole, light hole degeneracy, because now we're quantized on the Z direction. And due to the different masses of light hole and heavy hole, they have different quantization energies. Then we have the effects of strain, which I've already mentioned. And you can see when we compare bulk gallium arsenide to the 30 nanometer strain quantum well, they're quite radically different. You see a shift of the band gap. You see these rapid inversions of the nuclear polarization, very dramatic oscillation in the sign even. And now I'll go to the band structure calculations. The nice thing is from our NMR strain gauge, we can infer the strain in the observed region of the sample, convert that to a strain that's on the order of 5 times 10 to the minus 4. This strain can then be put into the electronic band structure calculation. And the Stanton group does these 8-band Pigeon-Brown model where they calculate the absorption. I'm going to have to go a little fast through this, and they can calculate. Okay, I'll go back here and point out this is the optical polarization. These are the matrix element from the initial to the final state as a function of K. These are the difference in the Fermi functions of the initial and final state, and this is the absorption line shape function here. It all goes in. And so you can see here in this actual calculation for our structure, now the splitting of the light hole and heavy hole, and you can see the fan diagram of the Landau levels. It all comes out of the calculation. The nice thing about theory is you can calculate the absorption to just spin up, for the spin selective transition to spin up or spin down. And from the absorption you can construct the conduction electron spin polarization in this fashion. And then we use the model to connect the electron spin polarization to the OP-NMR signal. It's going to obviously depend on the total absorption. If there's no absorption, you're not going to have optical pumping. And then the deviation of the electron spin polarization from its thermal equilibrium value. Now, I'm not going to go through this entire table here, but I just want to point out that we have this particular terminology or nomenclature to label the specific transitions in the system. And if we look at the OP-NMR signal, photon energy dependence, and compare it with the theory, the nice thing is we can now assign particular features in the OP-NMR photon energy dependence to particular optical transitions, T1, T2, T3, and you can actually see the contribution of these different transitions to the observed OP-NMR signal. So that brings me to the end of my talk here. Just to summarize, we've been able to account for the strain relaxation using a mechanical Boeing model. For the quantum structures, we see the calculated spin polarization agrees with the sign and strength. We get, I wouldn't say quantitative, but qualitative agreement. Specific Landau levels transitions can be assigned to the OP-NMR features. The interesting sign change in the OP-NMR occurs near the light hole transition in the quantum well, which is not seen in bulk, this inversion of the nuclear spin polarization. At the quantization, combination of quantization and strain have the effect of really peaking up the photon energy dependence and giving much more dramatic features in the data. And finally, and so that's basically what I just said. The strain enhances these effects in the quantum well systems. Okay, so at that point, I'll conclude my talk and be happy to take any questions.